Yeah, hello everyone. So I've been introduced, but like, if you don't know me, you maybe have seen that avatar somewhere on GitHub. So I usually goes by Root. That's probably how you know me. And also, just like before I start, like just a quick forwards. I usually don't give talks. I hate that. It's very stressful and all that. But like, I really like the hot take idea. So I really lean into it in this talk. But I just want to be clear that it's very fun in games to give hot takes. But ultimately, we're engineers. We're supposed to like. I don't have hot takes at work. At work, I'm like nuanced, and I talk about trade-off context. Sometimes it's better. Sometimes it's worse. Things. Still. It's fun to go with hot takes. So what I'm going to talk, like this talk was going to be about, is a different perspective on what you usually hear about concurrency in Ruby and like what to deploy and things. You may have heard that Unicorn is like the old way of doing things, and that the only reason you will use Unicorn is just because you started with it and you're not thread safe, so you cannot use the modern stuff like Puma, and that's probably why you're stuck with it. But the modern way to do things is to use threads. It's way more performant, or even more modern is now fibers with like things like Falcon and stuff, and it's even more performant than threads. The state of like the Ruby community right now is that, this is from the Ruby on Rails community survey. Too bad is they're doing the 2026 version right now, so I don't have the data yet, but you can assume the trends are the same. And just by a show of hands, is anyone running anything other than Puma in production? 1, 2, yeah. Iliana, you should raise your hand, but whatever. So you can see that like starting from like 2014 or something, just Puma just took over the Ruby world, and that previous servers like Passenger and Unicorn just started like taking a dive. And if you're curious about Falcon, that you may have heard of recently, it's just a teeny solo orange dot on the bottom right, so it's quite confidential still. And the reason why everybody uses Puma, aside from everybody else is doing it, so therefore I do the same, is that it kind of started with Heroku, because Heroku used to be built specifically for Rails and will do like buffering of requests at the load balancer layer, and then ensure that your app processes would get only one request at a time. And then toward 2010 or something, they just changed all that, but a very dumb load balancer that just forwards everything immediately without buffering or anything. So you had to defend yourself from what's called the slow loris attack. So it's just a very simple attack pattern where you open a connection and then send the request like 1 byte by 1 byte over a very long time, and you just tie the process forever. And so what was the standard of the time, which was Unicorn, was very vulnerable to that. You're meant to deploy it behind a reverse proxy like Nginx to do the buffering and all that. So since Heroku was the go-to way to deploy Rails, and people choose a server that's work well with Heroku. Also, if you want to have like a bit of fun, you can look at this blog post from Rap Genius around 2013, which made a lot of noise back in the day about like them discovering all this problem. So the Puma is designed about several assumptions that you may have heard across the board, is that using threads allow you to use less memory, which is important on Heroku because you don't have that much memory there, at least on the default dynos. And that your web application are basically just a proxy to the database. They don't do much except doing SQL queries, so you don't mind about the global VM lock. I'm going to talk more about that later if you don't know what it is. But it's fine. Like, yes, Ruby cannot do parallelism, but it's okay. It's all IOs anyway. And also, possibly, like, Puma was started by Evan Phoenix, who was also the author of Ruby News. So for those who are new to Ruby, like, 15 years ago, it was like an alternative implementation of Ruby, quite experimental, but was meant not to have a GVL. So they really wanted to design a server that was much more performant for their use case. Or at least I believe so. I cannot be sure. Yet, what may surprise you, like, this is not necessarily public information. You can know about it by talking to people who work there and whatever, but like all the big Ruby shops, and I mean being by like traffic size and like app size and all that, they all use either Unicorn or like Pitchfork, which is a fork, like a derivative of Unicorn. I started at Shopify a few years ago. So yeah, like Shopify, GitHub, Zendesk, stores, like all these things. Gusto is also on Unicorn. Intercom, my current employer, is using Passenger, but in single-threaded mode, so it's very similar to Unicorn. The only notable exception I could find was GitLab. There might be others I didn't find, but like, if you see like a very big Ruby shop, chances are they're running some form of that. I put a little asterisk on Shopify because you may have heard that they deployed Falcon in production. The reality is that it's like one app for certain path. For 99% of requests, it's Falcon in like single-threaded mode, sort of, so it's very much Unicorn still. So yeah, the first hot take is like server benchmark, because people sometimes choose their server looking at like Tech Empower benchmark or other like macro benchmark like this, and it's absolutely useless. As a case in point, I was bored in an hotel room like a few months ago, and I just decided to optimize Puma with a very nice like 17% faster on benchmark. But the reality is like 17% faster means like half of a microsecond, which is your app is likely answering in like 50 milliseconds if it's well optimized. So like it's just, you cannot measure that. It's absolutely, nobody cares. Nobody's ever going to see it in a real world environment. The main differentiator between like Puma, Unicorn, and all these things is really how your code is executed, like all your concurrency and parallelism primitives are. Puma and Passenger will be able to do an hybrid of process and threads, so they will have a number of processes, and within each processes they would have a number of threads. You can put the number of threads to 1, and then in that case it's equivalent to Unicorn and Pitchfork, which are just doing plain processes. And then you have like Falcon and possibly other things I forgot, but who are like hybrid process and fibers. There's not really a best one. It really depends on what your app is doing, what exactly, but like the main impact of that choice is the operability of your service. And if you don't know what operability is, that's what the rest of the talk is going to be about. I lifted this definition from Wikipedia, I think, but the crux of it is like, it's nice to make a prototype on your machine and whatever, but like once you send it in production, you need to ensure that it's going to continue to behave as you expect it to behave, even when you're going to have like spike of traffic, when you have like a database going down, all these things like that. You want to be able to work with your service in production and not just say like, oh, it's a black box, I have no idea what's going on, and I'm just going to pray that things go back to normal. So in practice, it's like stable and predictable latency, as in like your response time, as in like if you have an endpoint, you optimize it well, it responds in like 20 milliseconds or 50 milliseconds. You want that for the vast majority of time, it's really that number and not like randomly it takes 2 seconds, because this is really hard to deal with and really problematic. Also, resiliency is just like if something fuck up, like if you have a large team of developers and they ship features very fast, they might introduce bugs. You might say like, oh, just don't introduce bugs in production, but that's easier said than done. You want that when those bugs inevitably happen, that you don't crash everything and that it's just keep on working. Eventually, just the feature that has a bug is broken and not the rest of the app, this sort of thing. And also resource limits. If someone introduces, like, say, a memory leak or whatever, what's going to happen? Like, are you going to get paged at 3 a.m. or is just going to keep on checking is the question. And finally is fast and reliable deploys. Like, we don't think enough about that, but like an app like Intercom is deployed every like 5 to 6 minutes on average, like during the working hours. We deploy, like, the app is in constant state of like being restarted and replaced and all that. So it's not just like, oh, my peak performance or whatever. It's also like, how easy is it to roll out a change? If the change is bad, or is it how easy and fast is it to roll it back? These sort of things. So just to give you an example of like 2 somewhat concurrent patterns that are more or less operable, is like, say, like the classic fast transactional HTTP. By that I mean like you do a GET request, you get your answer, you do a POST, you get your answer, and nothing like like a long polling or anything like that. That has like perfect operability because there's no state in the request, so you can just Potentially, you can retry it if you know it's a get and you trust your app not to do stupid things on the get. You can just, if you hit a server that cannot respond, you can just send it on another server. If you need to deploy, well, that's easy. You just stop accepting requests. They're sent elsewhere. You restart, and then you accept again. It's really, and also if you have a bug in production, it's usually like self-contained is a request. Of course, you have the cookie with the session and all that, but like it's very easy to take a production request, replay it on your machine, and all that. Whereas, like say WebSockets, which you also do in your browser, is like way harder. Like you cannot, as a proxy or as an app, as an operator, as an SRE engineer, you cannot assume much about what's going on inside a WebSocket. Like if you need to deploy an app that mostly talk through WebSockets, like how do you know that it is safe to close the connection right now? Like, are you like in the middle of the transaction, or is the client gonna behave? Is it gonna reconnect? Is there gonna be like data loss or something like that? If you need to load balance, like, or you're out of capacity, you need to bring more server online, you're not going to be able to redirect, like to migrate one live socket from one server to the other, right? You need to close it and reopen and all this sort of thing. So you can rebuild the same sort of operability than you have with like transactional HTTP, but you're going to have to build it custom for yourself. You won't have like, I don't know, Nginx or Varnish or all this sort of middleware you can use. Another example I could have used is Memcache versus Redis. Like Redis does everything Memcache does, but more. And the problem is like if you actually only need the feature set of Memcache, you're much better putting Memcache because it's much more predictable. If you use Redis just for cache, and then one day someone starts using more complex commands, you might start having like slow commands, and then suddenly your Redis server takes 50 milliseconds to answer a very simple GET query. At least if you go with Memcache, you know exactly that it cannot be abused. There's much less way it can be abused, and it's interesting. So yeah, a consequence of all that is that a service is only as operable as its least operable part. So if you have, like, say, a big monolith with only transactional HTTP, and then you decide to say, like, oh, I'm going to add some WebSocket capability into it, no, suddenly your entire monolith is as operable as like a WebSocket app. You just lost all the advantage you had. So that's why, like, it's better when you do these things, like when you have, like, by design, you need less operable parts. It's a good idea. It's actually a good use case for not necessarily microservice, but like for an external thing, like action cable or any cable. You can like host them separately. You can make it transparent from the client by having like a reverse proxy that redirects the things or whatever. But like there should be like different services, like different processes on your server. So that's why it's very tempting to say like, oh, with Falcon I can do both WebSocket and transactional HTTP in the same process. And you might think it's going to be simpler to reason about, but actually you're going to bring a lot of problem onto yourself. This is not to say not to use Falcon. This is to say to use Falcon for the WebSocket and stay with something simpler for the vast majority of the rest. And so, yeah, the point of my talk is to showcase how multiprocessing, as in like Unicorn, Pitchfork, and all that, maps very, very well with transactional HTTP, which even today, where I know more people are doing more like talking to LLM APIs that are like drip feeding tokens and stuff. So you have more use case for sort of like more asynchronous sort of patterns, but still, usually, even those apps will still have a lot of classic transactional, like CRUD sort of pattern, but you may want to keep on a much simpler, much more easy to reason about sort of pattern. And yeah, multiprocessing make it very easy to reason about because since each process handles one request at a time, you have much less sort of like noisy neighbors sort of situation. Your requests are isolated, so you know that they won't impact each other in weird ways. I'm going to dive into that a bit better. So first, I mention it better. Like I need to disprove a bit the idea that Rails apps are just IOs. They're just a thin proxy to the database. I wrote a blog post about that, the mythical IO bound Rails app, where I argue why I think it's not the case, and then later on, Datadog published some profiling reports they got from like all their customers running Ruby that just basically proved my points. The graph on the left is a bit hard to read, but basically what it says is that only 16% of the application that were profiled by Datadog, it's a large pool of application, only 16% of them had, were doing less than 40% of CPU per request, and only 3% were doing less than 20% of CPU. So you might wonder, like, why do we care about that? Well, we care about that because of the GVL. So the GVL, you may have heard of it, is something inside the Ruby VM that prevents two threads or two fibers from executing Ruby code at the same time. It means you can have parallel IOs, but you cannot have parallel CPU execution. And you can see on those two graphs, like the graph on the top is a timeline of how two concurrent requests behave inside like two threads inside the same process. And so, for example, you can see that the second thread is doing a bit of CPU, then it's doing a bit of IO, and then its IO is done, so it would like to, you know, maybe did an HTTP request and now it wants to parse the resulting JSON or something. And you have this GVL wait time slot, because this is when the thread could have processed the response, but can't, because the thread number one is still doing CPU, so it has to wait. Whereas with process servers, you don't have that problem. Like, they just can, as long as you have like 3 CPUs like core on the servers, they can just run in parallel, no problem. Another case of contention is GC. Because when a thread allocates, at some point the GC is going to say, okay, you allocated too much, I'm going to stop, I'm going to try to make some space. And that to like just stop all your fibers, all your threads and stuff like that. So if you have like one request that is very allocation heavy, and you have like one super optimized request that end up in the same process, 2 different threads, your super fast endpoint that normally takes 20 milliseconds will sometimes take like 2 seconds because GC triggered because of another thread. So the problem with this idea that rails up our IO bound and therefore it doesn't matter, you can use more threads, is that it's a self-fulfilling prophecy, because the way most IO, like most applications are instrumented to say like, oh, I'm doing that many percent CPU, that many percent IO, is that before you do any IO, you just record the time, you do your IO, and then when you're done, you record the time again and you do the diff, and that's your IO time, basically. That's a teeny snippet on the top right. The problem is that this is a lie, because actually, when you start doing your I/O, you unlock the GVL, and then when you're done, you try to reacquire it, and you might wait, that's what I showed before, for a very long time. Another thing I don't show is that typically for database query, once you're done doing your I/O, you're just going to do a bunch of CPU to parse the answer, and then you're going to allocate a lot of Ruby objects like strings and arrays and hash to just give the answer. And that has a high chance of triggering the GC. That's even further going to slow down the thing. So your recording of like time before and after is I/O plus GVL contention plus GC plus the parsing plus all that. So it's not purely I/Os. It's some I/Os, some CPUs, some contention. And the problem is, if you're convinced your app is I/O bound, and so you use, I don't know, 3 threads, and you measure it, and you have a GVL contention or something like that, you're going to see, indeed, oh yeah, it has lots of I/Os, therefore I can use more threads. So you crank up the number of threads, and then you even more contention, which is going to be reported as even more I/O, and so you're going to see, oh, it's pretty problematic. In Ruby 3.2, for this problem, I added like a C-level API that allows you to instrument how long each thread wait for the GVL. So now some APMs started to report it as well. I think AppSignal, I'm not sure. So now some APMs show you that better, that you have like thread contention and should be using less threads. It's going to get better. You also sometimes hear that fibers don't have the problem with GVL contention. This is true because they don't try to acquire the GVL, but also they won't be scheduled unless the GVL is free. So it's the same problem, really. It's just that it's harder to measure with fibers, but same problem. Yeah, I already explained. I already explained most of that, but yeah, the consequence of the GVL contention is that your latency is going to get worse as your system gets more busy. So you might think, okay, right now I'm doing, I don't know, 1,000 requests per second over that many servers, and it's only using like 2 or 5 threads on my Puma servers. Therefore, I can, scale to like 2,000 requests per second because I'm not using half of my capacity. Except that your server is going to be slower if more capacity is used. So your capacity planning computation is much more complicated than that in reality. And also, you probably never tested your application as in like fully busy with like all 5 Puma thread busy and stuff like that. So it might be that you're going to accept request in, but actually all your query is going to be slower and whatever. You're going to start eating timeouts, and actually you're just not going to serve your app slower. You're just going to time out everywhere, and you're going to give 500s or something like that to your customers. So that's why it's better for transactional HTTP at least to have a clear idea of like how much concurrent requests you can actually handle, and if you get more than that, you just queue at the load balancer, because that's allow you to potentially bring up auto-scaling, so get more dyno on Heroku or something like that. And that also allow you, if worst case scenario, you're just gonna drop some of those requests to ensure that at least the one who got in are served properly instead of everybody having errors and timeout and stuff like that. Also, as I mentioned before, Ruby's garbage collector is top the world, so whenever the garbage collector starts, like everything stops. I mean, if you had IOs already scheduled, of course, they're going to continue, but like all your running threads going to stop. So that's what I explained a bit before. If you have a request that very heavy, allocates a lot, triggers GC a lot, it's going to degrade the performance of well-behaving requests, which you don't want to see, because if you're trying to improve the performance of your app and you're measuring like an endpoint performance, you're going to start to see like, why is this endpoint normally super fast and suddenly like takes 2 seconds? And it's going to be super hard to figure out, because if you trust your request, you're going to just see like, oh, why is this query taking so long sometimes? Well, it's because it happened to run at the same time as another request on that same server, same process. So in theory, by using multiprocessing, you're running GC more and you're doing more work. But in practice, that's not really the case, because Ruby's GC is generational. I'm going to explain that. Generational means that every Ruby object is split in 2 categories, either young or old. The theory is that most objects die young. You allocate an array, you do a bit of computation, and then you have a resulting string or whatever, and the array, you don't need it anymore. This is important because, contrary to what many people think, GC are actually extremely performant. Often, for some use cases, they're more performant than manual allocation, in that the time GC takes is bound to the number of live objects, not the number of allocated objects. So if you allocate like 5 gigabytes of memory, but you never use it, the GC is going to run as fast as if you allocated nothing. But the problem is like the Ruby generation are relatively low. If an object survives 3 GCs, then it ends up in the old generation. And the difference is that when Ruby GC trigger, normally it triggers a minor GC, so it only looks at young objects. So in practice, what it means is like you have your Rails app, you might have like 200 classes, you have like maybe some static data that's in your heap. The Ruby GC is never going to look at that because they're old, and it's never going to waste time, and you're going to be able to, like I worked on an app before that had like a 5 gigabyte heap, and we could run minor GC in like 3 milliseconds. That's no problem. Except the problem is, since an object is promoted quite fast, if you have like an endpoint that triggers GC more than 3 times, the transient objects that normally would have been gotten rid of at the end of the request end up being promoted to the old generation. And now you need to run a major GC, which look at every single object. And on the app I was talking about, a major GC was more like 3 to 4 seconds. So if your time budget for an endpoint is 15 milliseconds, you understand that like a 4-second pause is just not acceptable. So that's why we at Shopify we developed like a new feature in Ruby, which is allowing you to control when a major happens. So the idea is that in a web application you have as I said, like all those old objects that are your code, your static data and things that never change. And then you have everything you allocate during a request cycle that you never keep at the end of the request. So you want the first category to always be old and the second category to always be young. And if you can ensure that, then you almost never need to run a very slow major GC. And so that feature in Ruby allowed to do just that is you say like, okay, from now on, you never run a major unless I told you so, and you never promote an object to the old generation either. And this ensures that you're never going to have like those short-lived objects be promoted to the old generation. And this works perfectly with the web request cycle of like, I allocate a bunch of stuff, I throw it all out. But that you can only ensure in a single request per process thing. If you're having concurrent requests, you never have a not of band sort of time because you have like interleaved requests. So just to show a bit of data, so I did blog about it on the Rails at Scale blog at the time. I don't know if you can see very well, but basically like it just dramatically reduced the amount of time spent in GC per request. So it's like we reduced, like we would sometimes have like pauses and like it reduced them by half on average, and particularly like it's barely visible here, but like this is a P99, so it's a really tail end latency. So it really solved the this endpoint sometimes takes 2 seconds and we don't know why sort of problem. One of the very first things I did when I started at Intercom was basically to set up the same thing. Here again, it's not very visible, but like the blue line is without OOBGC and the green line is with. It's not like the scale make it less impressive, but really it's very stark change. Another big benefit of the multi-process model is what do you do if one of your web requests just is stuck or seems to take way too long? It can be because, I don't know, it's hitting a third-party API that is having an outage, or maybe your database is having an outage, or maybe it's a bug. You end up in, I don't know, an infinite loop. Might be sounds stupid, but I show you if you send enough code in production, you'll see it. Well, the problem is like with a thread or a fiber, you just cannot safely interrupt a thread or fiber. What you can do is use, so timeout.timeout is a module in the stdlib. I included a bunch of blog posts from 20 years ago or like 15 years ago. It's seen as like, don't do this, basically. All they work is that they use either thread or fiber arrays under the hood, and the idea is that you send a signal to the other thread to, as soon as it gets just a chance, like raise an exception. Which means that no, if you're starting using that, you can have exception raised about anywhere in your code base, and I can ensure you no code is tested for that scenario. So it can happen that you raise in an unsure block where you were supposed to unlock a mutex, or you were supposed to close a file or whatever, and it's not happening that one time when you have a timeout. And then what it means is that you can use that, but if you did use it in a process, honestly, ERB Dragons, you absolutely don't know what's going to happen after. That's why, like, if you're running Puma in production, you might be running like the rack timeout gem, and that gem use timeout like that to interrupt your request. But it also has a very highly recommended option of like, after we did this, we just ask the Puma worker to shut down, and we're going to recycle it and get a new one that we can trust. Whereas in multiprocessing, it's like super easy because you know you're only impacting one request, and you can just use Unix. You just kill the process. It's reliable. It's never gonna not work. A process cannot possibly survive a sick kill, and you cannot possibly leak resources or anything like that. Like the kernel is gonna take care. I mean, you can, but like the kernel, 99% of the time, the kernel is gonna take care of everything. And then you're still going to have to pay the cost of like respawning a new worker with a new fork, but it's not that bad. You don't want this to have to do this for every request or whatever, but it's acceptable. Another thing I mentioned before is memory limits, or like memory leaks. The multiprocessing model, again, gives you the out-of-band sort of hook. You can do something after every request when you're not impacting user experience. You know, like I'm done sending the response to the user. Now, what do I do? So a thing I do a lot in multiprocessing like that is say like, okay, OAuth can use 1 GB of memory. And after every request, we check, or every 10 requests, you don't have to do it every time, but like regularly we check, okay, are we over our memory budget? If yes, maybe we have a leak, or maybe it's just like it blowed, something happened. You know what, we're just gonna exit, get a new worker, a fresh one that's used less memory, problem solved. We just report, we emit an event or something so we can see that, oh, it's weird, like that, starting from that day, we're starting to have much more of those events, and so perhaps we introduced a memory leak or some other problem, and now we can investigate, but we have all the time in the world because the system is still resilient to that problem. If you're in a multi-threaded or multi-fiber server, you cannot really do this because you don't, I mean, you can do it, I guess, but the problem is, what are you really measuring? Because the memory is like, is it leaked memory, or is it just the other request that allocated a lot and it's going to be released at the end of the request? You don't have a good idea of like where you are. And yeah, the main argument, as I mentioned before, like the main reason people went for thread is like, oh yeah, multiprocessing uses too much memory, because when you fork a process, you copy everything. Well, it's not true. You don't copy everything. You have what's called copy and write, as long as it's per memory pages. But like if you have memory pages that are read-only, the kernel is not going to copy them. It's just going to share them automatically. So in the end, like the multiprocessing memory usage is only a problem at the very small scale. Like if you use a basic Heroku dynos with half a gigabyte of memory and half a CPU, yeah, of course, it's just you're not going to be able to share much, and so that's going to be a bit too expensive. But if you're using either pricier dynos, or you're self-hosting, or you're on EC2 or whatever, I think in most places you're going to get 4 gigabytes of RAM per core. Maybe if you use like CPU optimized nodes on Amazon, you're going to have like only 2 gigabytes. I guarantee you with copy and write and that much memory per core, even the biggest monolith I work on, which again like Shopify monolith, 5 gigabytes of heap, well, in practice, a Shopify web worker was using less than 1 gigabyte of actual real memory use once you account for copy and write. So absolutely nothing, it fits in there, no problem. So yeah, the crux of the thing is like, if you're using multiprocessing, you want to use larger machines. You don't want to have 100 one CPU machines. You want to have like, I don't know, 4 25 CPU sort of thing. So you can achieve those economies of scale. Also, a misconception is like, I do want to do like concurrent, like, I don't know, I want to do like 10 HTTP queries at the same time, concurrently or whatever, therefore I need to use an evented server or whatever. Well, no, you can absolutely do that from Unicorn or from Pitchfork or whatever. You can still use async, you can use all of that inside your process. You can also have like background threads that are doing some sort of, you know, like if you do telemetry sort of things, you can just unqueue something in memory and have a background thread just like emit them on a periodical sort of thing. Active Record no support like async queries, so you can have like a future of like you just like fire a query and you get the result later, so you can do something else in the meantime. And soon, hopefully, like crossing my finger, but Raptor should be out of experimental status by December. You may even be able to do like CPU parallelism inside your process using a bit of Raptors. But again, as I said in the beginning, it's like there's huge advantages to multiprocessing. That doesn't mean like, oh, I'm not saying everybody use it now or whatever. There are absolutely use cases. There are absolutely apps that are truly IO dominated out there. According to Datadog, that was 3%, but still a use case. So yeah, you can absolutely do it. There's apps where copy and write doesn't work so well. There's a number of things. And also, fibers and thread are very useful if you do want to build something like action cable or whatever without having to say like, oh no, I'm gonna need to use Go or Node.js or whatever because Ruby can't. No, yes, Ruby can, thanks to fibers and thread and all that. Also on like whether I should use threads or fibers, if you're bold, you can go up to like 20, maybe 50 threads. After that, yeah, definitely use fibers. They're much cheaper. Otherwise, you're gonna have a problem. And yeah, just to conclude, just to throw a few things in the fire, I absolutely hate PHP as a language. It's like terrible. I don't like the syntax. I don't like the APIs at all. But its processing model is absolutely incredible. It's insane how fast it runs. They even have a JIT, even though they are like multiprocessing. It's quite crazy. And it works very well for the vast majority of web apps. Actually, I suspect the vast majority of web apps are still in PHP today. Like, there's probably half the web that is WordPress or something. If you're trying to sell me your new revolutionary sort of things, the SRE is speaking, I want to know how many times you woke up at 3 a.m. to fix it, because if the answer is 0, then I just don't want to touch it. I want to hear something like, oh, 20 times and it's been 2 years and no, it's fine. Then I'm interested. And yeah, just to finish, like, if you hear someone say like, oh yeah, we run Unicorn or whatever, they're just not left in the code. It's not outdated. It's not legacy. It can actually be very, very much cutting edge. I didn't talk too much about it, but if you're curious, go look at Pitchfork and Reforking. You can do very, very cool stuff with it. Thank you very much.